Good evening. Today we have our number 5 lecture on ship propulsion, ship resistance and propulsion. So please pay attention. I believe this is going to be a nice lecture for you. So now we are talking about propulsion. You must have seen this picture before, or even if you have not seen it, you can imagine it. Here we have, this is a propeller and it's working inside the water. You can see how it is throwing the water particles backward, and these water particles have momentum, and it is this momentum that is used to push the vessel forward. You can see that on this side of the propeller there's no flow, no scattered flow, no, that's what we call turbulence flow. But at the back here there's turbulent flow where it's exerting force, momentum. Okay, that is for this type of outboard engine. For this one, you can see how this area is before the propeller and then after the propeller. Before the propeller we have what we call wake. The first one, the wake is laminar flow, but here you see that the wake is not laminar flow, and this one have very little body in front of the propeller, but here the ship body is in front of the propeller, creating this type of what we call wake. The wake, and this wake around the propeller, you can see how it is throwing the water radially and axially backward. In fact, this particular propeller might be cavitating at the tip. We will deal about cavitation later. Okay, so we talk about wake. Wake speed is the difference, because the difference between the ship speed and the speed of water in way of the propeller, the speed of advance. This is what we call speed of advance. You can see that the water speed here can never be the same as the water speed at the bow of the ship. So this is the speed at which the ship is moving, which is the speed at the bow in terms of water, relative motion of water. This is the speed of relative, but here is the speed of advance of water around the propeller. They are not equal depending on the shape of the hull. Okay, when the shape of the hull is very fine, like in that case of the outboard engine, it's just a laminar flow. It's the same speed as the speed of the engine. But in the second case, where there was that turbulence, the speed is different, and this we have what we call the wake speed. Okay, from there, Freud now coined what we call wave fraction. Wave fraction, you can see it. Is the speed of the ship minus speed of advance divided by speed of advance. Now another great man in the fluid mechanics now defined this one, which is called also Taylor's wake fraction. So we have two wake fractions, from which we can see that this relationship between the speed of advance and the speed of the ship is given by this, while for the wake fraction, this for the Taylor, this for Freud, and this for Taylor. Okay, from which we derive that the wake fraction is given by this equation in terms of Freud wave and the Taylor wave. In your notebook you can see how this is actually proven, but believe me, it is exactly like that. Now the wake speed for single screw ship is derived to be of this order. See, it has this block coefficient factor, which is the shape factor, the form factor. Also, for double screw. Again, we go to the thrust. The propeller thrust T pushes the ship against the water. The resistance, as we saw before, against the water resistance, which is the resistance of the ship. The propeller creates a local water sucking effect. As the propeller is working, it's sucking water from on the side of the hull. You see, I will show you once more. You see, the propeller is sucking water from this side. It's sucking water from this side and throwing it backwards. As it's sucking that water, definitely there will be that suction effect will act against it's an augmentation, it's an addition to the resistance, and which is actually written as what? Thrust deduction. That's the difference between the resistance and the thrust. Actually, it's given as thrust deduction, from which we have thrust deduction fraction. You see, which is equal to this, or can be written in this form. The proof of this is given can be found in your textbook, but believe me that it is like that. Hull efficiency. Now you see that hull efficiency we saw before is PE over PT, which can be written as PE is RT and PT is TVA. Now you can see where I got the notion of the speed of advance. And if we will substitute all this theory about thrust deduction and wave fraction, you will find out that the hull efficiency is given simply by this equation. It depends on the thrust deduction fraction and the wake fraction. And wherever these are known, it means you can see how efficient the hull is in actually, mitigating against the thrust of the propeller. You can see that efficiency. Therefore, the overall efficiency, which is given by this equation, as I showed you before in the last lecture, can be written in this format. So, this is where the lecture today ends. Next time we'll talk about propulsive mechanism. This I would like you to go through, browse the internet, and be able to know all the mechanisms that are used in actually propelling the ship forward. Thank you very much.